Welcome everyone to another video on machine controls, and today we are going to look at the inverter a little bit more. I know we started looking at modulation techniques in our previous video, and in going through that, I felt like there was a little bit of a gap in how the inverter operates, whether it's whether if you apply it to a three-phase inverter or if you want to apply it to a bridge, an H bridge, we do need to understand some of the functionality and the different states the switch is going to be in. So I thought it would be beneficial if we can review or revisit some of these concepts and then build upon that before we go further down the road with the modulation techniques. Okay, so we are going to try to develop a mathematical relationship based on how the inverter is switching, and then we can use that material to go into a deeper analysis on how the different modulation techniques work. Okay, so that's the plan, and they may look like a little bit more technical or just the equation based, but they are very applicable to practical applications. And try to understand them, try to explain this to yourself. This way the concept will be more solid. It'll build up a better foundation for you in trying to understand how different controls, modulation strategies work. Okay, all right. And also I just presented at the conference, iTech conference, that was all online because of the current situation. So I posted that video for you as well. It's a little bit of a high level, research level topic, but if some of you do want to spend time trying to understand that, I would recommend go ahead doing that. Okay, all right. So here, this is a standard representation of an inverter, at least from a high level. If you go down to the hardware level, you're going to see a lot more detail. You'll see the gate drivers, bypass capacitors, bulk capacitor, all current measurement, a lot of other components that will go with an inverter. Here we are trying to set up the background to understand modulation strategies. So we need to understand how the different voltages are related when we apply them to a machine. Okay, so if you look at this inverter, we have MOSFETs, 6 MOSFETs, and you see the anti-parallel diode here, right? And depending on what a switch is on and what time, you will see that the voltage from ground to the phase. So these are the phase voltages for the 3 phases. They will be different depending on which switch is conducting. Okay, so now we are taking a very close look in terms of time-wise. We are zooming in because typically these switches are pulse width modulated. So they're going to be either on or off. Okay, but we're going to look at a very slowed down version to see to see what kind of different combinations can we see in terms of switching. Okay, all right. So right now we have to think of 2 different voltages that we are going to see in our motor drive setup. Depending on whether you have a battery or a power supply, regardless of that, you'll have a voltage with respect to this ground bus that is applied to the phase. Okay, and then this phase goes and connects to a motor. That motor will have 3 phases, and then for the motor, the connection of each of the phases, they'll have its own closed loop where you can apply KVL to analyze the voltages. So before we go that far down, let's first of all study what this VAG, VBG, VCG, these voltages of the phase with respect to ground would look like at different switch combinations. Okay, so that's the primary focus. So this is basically ground to phase or phase to ground voltage. not the motor voltage that we apply. Because if you are looking at the phase voltage of the motor, that is with respect to the neutral, if it's a Y-wound machine. So that's a little bit of a there's a little bit of a difference there, and we will see that when we go in, at least towards the end of this discussion. Okay, and then we know we talked about that these switches are being pulse width modulated. Of course, you can operate them in the continuous region, but they're going to be very inefficient. So that's why we use pulse width modulation. Okay, all right. So let us go look at the different switching states. Now, I used to learn using the Analysis of Electric Machines textbook by Professor Wawrzynczak and Sudoff from Purdue, and I'm going to stick to that combination for, at least for this discussion, because it's very clear, and we can look at how the mathematics are linked to the practical application. Okay, and there are other textbooks that may use different notation, different concepts in discussing this, but feel free to investigate them. I'm trying to follow this one approach, one textbook in going through these discussions. Okay, so in order to look at the different switching combinations, we will just use one leg for now. Okay, and we're just naming them X because it could be A, B, or C. All right, and then we have a DC bus voltage, we have a current that's going in the phase, we have a current that's coming from the DC link. Okay, because not all the time the DC current is going to be the phase current. You have to be a little bit more careful there. Okay, all right. So first combination, or first switching criteria is where you have the upper switch on. Okay, so you have your upper switch on, which means you'll have a switch drop right here. If you remember from your electronic circuits class, you'll see that there is going to be a little bit of a VDS when the switch is fully on. For a lot of theoretical applications, we assume that to be 0, but I'm just representing that for the accuracy here. And when the upper switch is on, we keep the lower switch turned off. Okay, if both switches turn on at the same time, you're basically shorting your DC bus to ground, right? So that's almost a dead short, which could damage your power supply or your battery. Therefore, typically we make sure the lower switch is off when the upper switch is on, or vice versa. All right, so in this case, and upper switch is on, and we can see that the current is positive. So the current is coming out. Okay, and in that case, we can say that VXG is basically what? VXG is VDC minus the switching drop. Okay, VXG, the voltage that applies to the motor with respect to ground, is VDC minus the switching voltage. Okay, so that is one case. So the current is positive. Now here, so here you can think of this as even the upper switch is on or upper switch off, with the current is passing through the diode. Regardless, there is no other way for the current other than the diode to go back. Okay, so this is a case where VXG is larger than VDC plus the diode drop. So we are sinking current back to the power supply. So this is, you can think of an example for this like a regenerative case, right? So you have current going back to the DC bus. Okay, and it's passing through the diode, hence you see the diode drop. All right, okay, and then there can be another case where the upper switch is on, however the voltages are equal. VXG is equal to VDC, therefore no current, so almost equal, so there is no current flow coming out or going in. Okay, so that's the upper switch or the diode is on. And then you can see three cases or three similar cases for the lower switch. You can have the bottom diode on, okay, and then that means there's current passing through. Current is positive because the diode is on. That means the voltage at the phase is negative with respect to that ground terminal. Okay, ground doesn't mean true zero. Just keep that in mind. Now, and then this case where we have current going back in, current is negative. So in this case, the switch is on. So there's current passing in to the DC link or DC power supply. Okay, and then here the third case where there is no current passing. However, either the switch or the diode, one of them is on because we have the voltage of Xg being equal to the DC bus voltage, right? Yeah. Okay. Now we do need to keep in mind there's a concept called dead time when you turn the top switch. So it's a sequence, right? Whether this is on or this is off. And when one switch turns on, let's say the top switch turns on, and the period before the bottom switch was on. So when you do that, you want to have enough time between the turn-ons of the individual devices so that there is no interval that both switches are on this same time. Okay, that way you can prevent shoot through, and that's called dead time. Dead time. Typically, this can be programmed in your software. Okay, and then this is a kind of odd different cases, but you do see them in your inverter system. So here neither switch is on. This is similar to the diode conducting. So this is the bottom diode conducting, and then here this is the top diode conducting. So current is being fed back, and this is a very rare case that you see where you see that your both the power supply, the DC bus, is split between because there's no current flow and neither switch is on. Okay, so neither switch is on. So it's very difficult to get a really good idea about the voltage here. So we typically assume that the voltage of the DC bus is equally split, and this situation or this condition doesn't occur very often. So but just in general, we have that condition in case we need to model a certain phenomena. Okay, so these are the three the different combinations you'll see for any switch in this three-phase inverter system. All right. Okay, so now we need to think of the line-to-line voltage. Okay, line-to-line voltage, because here in our so if you go back to our inverter, line-to-line voltage is basically the voltage difference here, right? VAG minus VBG, that's the line-to-line voltage, and then you can consider B to C or C to A. That's what we call the line-to-line voltage. Now, we typically represent them VABS, VBCS, VCAS. So that those are the line-to-line voltages. And if you think of DC current, the total DC current is the sum of all the currents at any point in time, right? Sum of the three currents. So we represent the DC currents in this way. Now, considering that most machines are Y-wound, they'll have a neutral point. Those machines will have a neutral point. Now, the voltage that we typically consider as VAS is the voltage from that phase A to the neutral. Okay, same goes for B and same goes for C. Okay, so we consider the phase voltage not the line to line voltage. So typically we call this is the line to line voltage and this is the phase voltage. Okay. All right. So let's get a better idea of the relationship, because we need to understand these concepts a little bit more as we go further down the road. Now, if we just consider one phase, I want to highlight a very important point here. So if you look at the phase voltage, and if you look at the phase to ground voltage from the power supply end, so this is the phase to neutral, this is phase to ground. Okay, so this is a conductor. Sometimes there is a current measurement resistor or current sensor there. However, see that these two are different. These two, the neutral and the ground, they are different in this case, right? So potentially there could be a voltage on the neutral point with respect to the ground. Okay, with respect to the ground. All right, it could be tied to true earth ground, it could be just a floating ground, but for our discussions this is going to be the reference, at least for now. Okay, so with respect to that, you're going to have a certain voltage to the neutral, and that voltage might be zero. We don't know that yet. So this is the reason that this is important, is this is where the modulation strategies come into picture. When we go further down, we'll see that having the ability to somehow modulate or vary the neutral point voltage will be great advantage to us. Okay, all right. So so this is the relationship, and then if you look at VAG, this voltage, if you simply apply KVL, this is equal to VAS plus VNG, right? So these two voltages, the sum of the two equals VAG. VAG is what we apply by using PWM. We do the modulation as we discussed earlier, and then we apply that voltage to the phase, and then depending on the modulation strategy, we can determine what that VNG is going to be. Okay, all right. So now what I want to do is, so let's look at the following relationship. Okay, so let's add the three voltages. Okay, let's add the three voltages VAG, VBG, and VCG together. Okay, VAG, VBG, VCG together, because we are now trying to come up with a value on what VNG is going to be. We are trying to get an idea for about what VNG is. Okay, so when we add the three voltages, we have the phase voltages plus 3 times VNG. Okay, so when we consider VNG in terms of phase voltages and bridge voltages, we get this relationship. However, now VAS, VBS, VCS, those are voltages that that are in the machine, and if they are balanced, which is most of the case, the sum of the three is going to be 0. Okay, we call this the zero sequence voltage. Zero sequence voltage. Okay, and for this to be 0, it has to be balanced. The machine has to be balanced, and the voltages has to be balanced, 3-phase balance set, and then this will go to 0. You can even prove this mathematically. I think I may have proven this in one of the previous classes. Okay, so you can set the zero sequence voltage. Now the zero sequence voltage is 0 for a balanced machine when you apply the 3-phase voltage. Okay, so which means our VNG, the neutral to ground voltage, ends up being 1/3 of VAG, VBG plus VCG. So we have an idea of what that neutral to ground voltage is going to look like. Okay, is it 0? No, we don't know that yet, right? So we know that we can come up with this relationship. Okay. Now, with that, if we go to our first equation for VAG, right, we can say that VAG is equal to VAS plus VNG, right? We derived that from that initial KVL by applying KVL, right? We came up with this relationship. Now I'm going to rewrite this a little bit differently. So let's get VAS. Let's see what VAS is. So VAS ends up being VAG minus VNG. However, we know we have a relationship for VNG, right? We just obtained that in the previous page. Now we can substitute that to our equation here, right? When we do that, we have the following relationship for VAS. So VAS based on the bridge voltages is going to be like this. So all three phases contribute to make up our VAS voltage. See, all three phases. So 2/3 of VAG minus 1/3 of VBG minus 1/3 of VCG makes up our VAS. Okay, and you can even try to visualize this a little bit. So if you look at the inverter and the machine, right? So I'm going to draw it a little bit differently here. Right? So you're applying voltages to each of the phases, and then we are looking at this voltage. That's the VAS that we are interested in. Okay. So those voltages, VAS, VAS, or VBS or VCS, they are a combination of the inverter output voltages. So if we go back to our inverter here, right? This is VAG, this is VBG, this is VCG. And that phase voltages are related to all three. So the combination is what results because of that electrical connection that we have inside the machine. Okay, because we apply VBG here, VCG here, right? VB, VC, and with respect to ground, all with respect to ground. And then there's a neutral point here that gives us this nice relationship. Okay. All right. Let's see. Yeah. So this is a good point for us to stop right now. All right. And the next one, I'm going to go over a little bit more of modulation, and then how we can convert the sine triangle method using this relationship, and then we can look at third harmonic injection. Okay. All right. Thank you, folks.